things you have to know. First thing is, if I drop a copy of the cameras in a moving train, it doesn't fly backwards like the conductor. It just drops relative to the train. So, if anyone's conducting an experiment in a moving train or in the laboratories in Princeton, the results will always be the same. Because no matter where springs and rolls and balls are, he's there too. That's the first thing you have to know. The second thing you have to know is that light absolutely always travels at the same speed in all directions at once. 186,282 miles per second.
Point at 397.
Faster?
We got more accurate.
Don't confuse me. Now then, you have to imagine a man driving in a car at 30 miles an hour and a hitchhiker standing by the road waiting for a lift. Now, the car is traveling at 30 miles an hour. And the man inside the car throws a stone at the hitchhiker at another 30 miles an hour. Now he's the lead pitcher. So the question is, if the car is going 30 miles an hour and the stone is going at another 30 miles an hour thrown in front of it, how many miles an hour is the stone going when it hits the hiker? Answer, 60 miles an hour, right? Pretty straightforward. Well, now let's forget about the stone. Instead, we'll imagine the car is traveling at 30 miles an hour, and he, wait a minute, can't put the hitchhiker back. Imagine the car is driving along at 30 miles an hour. He's flashing his headlights with the hitchhiker, telling him to get the hell out of the road. Does the light travel at 186,282
397.
397 plus 30 miles an hour? Answer no. Why? Because the speed of light is always the same. Right? Did you ever prove that hypothesis?
It's never been disproven.
Yeah. Let's hope it never is. You ready? Here we go. You have to imagine two locomotives speeding past each other at a hell of a speed. A red one and a green one. Now, the driver of each train, you're the driver of the red train, turn on when I say go, okay? Has a flashlight. She turns on, and the next moment that they pass each other. Now remember, the light from the flashlight travels at the same speed regardless of the speed of the flashlight itself. So, each light, turn it on. Okay, go. Both lights. There you go. Yeah. Older. We must spare one. It's time as well. But you gotta what? Because you're gonna need it. Yeah. You have to imagine this room is the entire universe.
I like this bit.
We came together someplace in space-time. You synchronize it. What did your watch say?
8:15.
8:15. Right. I travel away from you at a hell of a speed. Say 1/5 the speed of light. And I travel for 5 minutes and it gets me here. Now, I look at my watch. It says 20 minutes so. I look across the universe. Check with your watch. And what does your watch say?
20 minutes past 8.
Not to me it doesn't. It says 19 minutes past 8. Because 20 minutes past 8 hasn't reached me yet. It takes a minute for me to see your watch. Because it takes a minute for the light to reach me. See, now comes the $1,000 question. Remember, if you look at my watch, it's going to take a minute for it to reach you too. So now what do you say my watch says?
19 minutes past 8.
Which means you say I'm going more slowly than you, while I say you're going more slowly, isn't it? So, 86,282.397 miles per second in all directions at once. The main point I've demonstrated is that all measurements of time and space are necessarily made relative to a single observer and are not necessarily the same to independent observers. And that is the specific theory of relativity. Isn't it?
That's true.